Okay, here we go. So, um, couple things here. The recording that I made in class, this is fall 2022, where we took the data from the manual and put it into Excel. What we did is we used commas, I think. Yeah, commas. And that video didn't come out so well. So, in principle, somebody watching this in future will see the original pre-lab video and use a tab delimited, but it's the same thing. But anyways, a couple things have happened since yesterday. One big thing is that, I'll just bring this over here. I rewrote the lab manual. And so this will really help you out, especially people in the future. But I wrote out much better objectives, much better backgrounds. So I would encourage everybody to take a look at this course. In future, you will be using this manual. I have posted this for the fall 2022 people. Okay, so let's get back to it, and we're going to be referring to different diagrams. I've had them in the spreadsheet, and I went over it yesterday, and I worked on it today. So we'll see. And I have the luxury of pausing the recording now if I start screwing it up. So let's get back here. So the first thing we did was imported the data and we made a plot, and then you might recall that I was weirded out because what happens is that the data, when you plot it, well, that's quite a number there. You see this a little different, but when you plot it, it comes out like this. And so, and I knew, then plot the raw data, and I noticed the spreadsheets had different values. In fact, something like here, and it's simply that it says right in the manual to add 52.5 degrees to it. And I finally, when I looked here, there it is. See, radians of degrees plus 52.5. And somehow I never clicked on that yesterday for the fall 2022 people. But today when I fired this up, being the uber nerd, I couldn't help myself. And maybe before I even noticed that 52.2, this might jump a bit. I'm going to pause for a moment. So when I first was looking at this today, and I was putting this together, I decided to create this rotation variable, and I decided instead of making it in degrees, I made it in radians. I may have put it in degrees at first. So you see in here, I'm taking the degrees here and turning it into radians, and then there's my rotation variable. And then I took it and I dragged it down, and I started experimenting. So at first, of course, it was 0 and 0.1, etc. Oops. Wrong one. This is 0.1. And you'll begin to see that it starts rotating. And so eventually I got to 0.9, and it looked pretty good. And then I was looking at this thing, and I said, oh, well, if I get it, because I want the ellipse to be such that the long part is lined up with the x-axis. And if I do that, I realize that if I take this like sort of like the residuals, if I sum up all the y values of all these points, that it's going to equal 0 if I have it rotate. And if the thing I vary is the rotation, the only thing I'm going to vary is rotation. Now, I want to point out to you that there is this document, ellipse properties for physics 1100 lab. It's just I took a Wikipedia article and I slashed and burned it, but all the variables I talk about, like A, B, C, E, the eccentricity, all that refers to this document. And it even says here in your background that you should use that document to make definitions for all these variables. Okay, so I tried the sum of the y's, of course. And one thing that's going on here, though, is that because there's this opening here, I knew there would be a little bit of error inserted into it. And but I thought, okay, there's enough points that maybe it wouldn't be so bad. And then I tried minimizing this, but of course I want it to be equal to 0, and then I forgot that I could have had the solver do that. So I just went ahead and created the sum of the y values squared. So there's the sum of all the y values. I don't have to do any, because there's no kind of residuals here. There's no fit function, but I know to center this about the y-axis vertically, I just know that all the y-coordinates have to sum to 0. And then I squared it. And so then I also, okay, so why did I do this? The min radius and the max radius. And that was the minimum and max. That was another idea I was having. And because it turns out that those things have a special value, and if nothing else, I know that the points with the min and max radius they're going to be the points that so remember the center is here, so approximately there's the min radius, and well, the max radius. In fact, as far as the data points, those are. They may not be the actual min and max radius. But I thought, okay, I'll use that to help me guide, and that's when I started typing in these here to try to rotate it, and so those 2 points were on the y-axis, and then I got the idea of using the sum of the y's and the y squared. So then I went up here to data, solver, and I said, okay, I want you to minimize the sum of the y squared, and the only thing you can vary is this rotation. And in this case, I don't want it to go negative, so I left it there. And lo and behold, I end up with this number, 0.89999, and notice it's 51.56 degrees. That's the conversion here. And you notice that it's pretty darn close to 0. And, you know, it's a pretty small number. And it looks pretty good. And so, wow, all right. And then, of course, I happened to look at the manual. You know, I've said it in class before, RTFM, read the effing manual. And then I got to 52.5. Okay, so then that is, you can turn that into radians. Let's see, radians. Oops, and I forgot to put equals radians of, well, I could just type 52.5 in there, but anyways. And then I can take this and copy and then paste that in. And now you see that's that rotation. It doesn't minimize the y squared, but they told us that 0.5, 1, 2, 3, 4, 5 should be on the axis, and in fact, it's not. It looks like it. So interesting, but we'll stick with that for the time being because we don't have really any other way of doing this. Well, like I said, it's the aphelion, so it really should sit on there. So let's see, why don't I do this? I can make this equal to that. And I suppose what I have to do is if I wanted to use solver, I could create some variable that would tell me that 0.5 when it's y, here's y right here. See, it's not quite 0. Huh? So I could do 52.3 if I really wanted to. And let's see, 0.5. The y value got bigger. Isn't that interesting? So, wait a minute. 1, 2, 3, 4, yeah, 0.5. That kind of weirded me out. Why would that, you would think that the y value there would get smaller and smaller. Well, I'm going to pause for a minute. I can't, I'm distracted. All right, well, look at that. It actually is 53 degrees, but I'm not sure what's right here. So for the time being, I'm just going to, I'm going to go with 52.5. And also, I figured out how to do this without counting boxes. So we don't have to worry about making the little tiny grid lines there. And anyways, another thing I did, though, is I wanted to calculate, so Kepler's laws, like the equal areas and equal times, means that when it's closer, it has to go faster, huh? So calculated, because I know the delta time is always 30 days, I got the delta theta for each pair of points divided by 30 to get the number of radians per day, and then I just used getting the average value of the two radius points to get the average radius in that interval, and that's sort of like the speed in the midpoint. And then I plotted the radius here and speed as a function of the radius. And you see, indeed, when it's close, it goes faster, and then when it's further away, it's going slower. Pretty nifty, huh? So anyways, let's get on with the rest of it. And the way I've got it set up now is that we can do all this kind of analysis. Well, this would be more like results because we're grinding data. And that's going to be our results, and then the analysis is taking those results. And this equation you might remember. But anyway, let's go back here. So we have the definitions here of the what's called the semi-major and semi-minor axis. So the semi-major A is from the extreme out here to the center, and the semi-minor and B is up here. And then there's this C, which is called the linear eccentricity. And then there's E, the eccentricity. And you can see from and this is all in that PDF, Ellipses for 1100 lab. You can see with this construction, pretty neat, without proof, I'm just presenting this, that we can determine C from A squared minus B squared. And then I don't have a picture of the eccentricity here. Oh, interesting. Let's take a look here. No, wrong. I want this. And I guess I want to see how we determine the eccentricity. There it is. Assuming A is greater than B, so yeah, but I want to know exactly linear eccentricity, but eccentricity, here we go. The ellipse may be defined as one, the is above mentioned, too bad. Well, here we go. The elongation of the ellipse. Yeah, I guess what that is it, no, this, I don't know. Let's see. I thought I knew that off the top of my head, but at least we know it mathematically. Yeah, I told you I wouldn't be hesitating and stumbling, right? But here I am anyway. Okay, so this is sort of just a copy-paste from before. And you see, I'm just going to use the 52.5 that they suggest, even though 0.5 doesn't have a y value of 0. And then just to, scaled. Okay, yeah, this is because I don't want you guys to just copy all this, right? So your data, just so you see, if I type a 1 here, so there is the graph from the previous page. The red is my fit line, and the blue is the Toro data. But everything I do here is going to work for you. Okay, so we need to get values for A and B and C and E. So what it did is, because now I'm assuming I have my graph rotated properly, and we're just going to take their word for it that 52.5 is correct. I personally am not convinced just now, but that's all right. Excuse me. And so what I did is then I looked for the minimum value of what's on the x-axis, which should be here, and the maximum value. And it turns out that the eccentricity is, you see I put G3 minus G2. You know what it is it's the total distance from those 2 points and divided by 2. That actually equals the semi-major axis. If you look on here on this, right? See A from here to there. And so that means that if I take the length, and remember everything's coming from this blue point, I take the length from here to here. I don't know what this A1 is. That's something that's dancing around. Oh, I'm sorry, I put that there. That's up here. I wonder what happened to A2. Anyways, if I got the distance from here to there, which is the min value of all the x values, and then the max value is from here to there. So I subtracted them. I was lazy. I should have. What would you do? Absolutely, yeah. You would add together the absolute values. Same thing. And then divide by 2, and I get an estimate, because the reason it's an estimate, because these points are not exactly on the x-axis. And in a similar fashion for the semi-major B, I get half of that. And then what I've done is these are going to be my fit parameters. You notice they're a little different because I've already done the fit. But so I'm going to copy and paste in these as estimates. And I'm pasting in the